In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. They are the freaks of the cosmos. Pulsars and quasars, so strange their very existence seems impossible.
They must be titanic, absolute monsters.
What makes them shine with the light of 1 billion suns, rotate faster than the blink of an eye, or bang out cosmic rhythms with the drummer from the Grateful Dead?
Once all of these things started to come my way, I realized that, the universe was singing.
But it's a tune bizarre beyond imagination, with pulsars and quasars, the superstars of an astronomical sideshow found only in the strangest sectors of the universe. In 1967, scientists on planet Earth made a startling discovery. Someone was sending us signals through space. Were aliens trying to send us a message?
When pulsars were first discovered, they blew us away. Something in the night sky was turning on and off. How could something in nature do that? And so we actually called them LGM objects, that stood for little green men.
Astronomers in England detected the signals using a primitive radio telescope, a massive array of poles and wires stretched out over 4 acres of land. The first of the signals was not just an isolated peak in the radio noise. It was a regular blip, precisely repeating every 1.3 seconds. Within a year, though, scientists realized aliens were not behind the regular signals. Instead, they came from rapidly rotating stars. Pulsar became the catchy name for the new phenomenon, short for pulsating star. A pulsar seems to blink on and off because the rotating star is sending out beams of energy from its magnetic field, which is not aligned with its axis of rotation. We see the beam as a flash of light when it passes across our field of view.
The beam coming out of a pulsar works a lot like this emergency beacon. Now take a look at how it flashes. It's not just blinking on and off. Inside the housing, the beacon has a rotating reflector that sweeps the light around 360 degrees. As long as we have line of sight with the beam, it sweeps by us every time it goes around. But it looks like it's flashing on and off. A rotating pulsar looks like it is flashing on and off for the same reason.
But a pulsar isn't just any kind of rotating star. It's a rotating neutron star, an exotic object created when a big, massive star ends its life in a supernova. Astrophysicist Pat Slane has a fascinating way to show us what's left over after the supernova, when the pressure of the star's remaining core can no longer fight against the force of gravity.
What I'm going to demonstrate here is what happens when we remove the air from the interior of this 55-gallon drum and let the atmosphere of the Earth, the weight of the air, crush it. This is similar to what happens at the interior of a massive star late in its life. When it loses its pressure support, the star collapses and there's a supernova explosion.
The crushed stellar remnant becomes the neutron star, with a mass 1.4 times our Sun, reduced to a sphere the size of Manhattan. It is one of the most bizarre objects in nature.
You have to understand that a neutron star is matter barely holding up before it collapses into a black hole. The gravity is so strong that it has crushed electrons into the nucleus of an atom and made neutrons. It's amazing.
If you take something like a sugar cube, for example, about a cubic centimeter, if this sugar cube were made of neutron star material, it would weigh close to 1 billion tons. Think of it as something like 8,000 aircraft carriers in something that size. Incredibly dense objects.
The newly created neutron star can't help having a high-speed spin.
All stars that we know about are already rotating, so when a massive star compresses into a neutron star, the rotation is compressed also. It's just like an ice skater. When an ice skater spins and she pulls her arms in, she spins faster.
The spinning neutron star is a massive natural electric generator. Its spin creates a powerful magnetic field. The magnetic force grabs onto electrons and other atomic particles and flings them into space at high speeds. High-speed particles always emit radiation, and in pulsars, they're coming out in beams. These are the pulses we see, but we see them only when the beams are pointed in our direction.
How many pulsars are known? It's something over 1,800, and the number is growing rapidly because we continue to discover new pulsars all the time. But the number of pulsars that exist, and these are all found in our galaxy, the Milky Way, is many, many times larger than that, because the beams that are seen in radio primarily are very small, and so we only see a tiny fraction of all the pulsars that are out there.
But each pulsar has a completely different rotational speed. The slowest rotates once every 9.437 seconds, and the fastest goes around 716 times every second. If we stood on its surface, we'd be going more than 97 million miles per hour. That's about 10 million times faster than we travel on Earth.
Every pulsar has an absolutely unique spin. It goes around at a given rate, and that's just like a fingerprint for an individual. So if you know what that characteristic spin is, then you know what that pulsar is.
Since all pulsars have their own signatures, you can use them as tools to determine your location in space, an idea that has been used by NASA.
Some of the spacecraft we've sent into the outer parts of the solar system, like Pioneer and Voyager, have had maps of space which show our solar system's location relative to the locations of a bunch of pulsars.
The pulsars in space can be used to locate the Earth in the same way that our GPS devices use multiple satellites to locate a position on the ground. It's hoped one day another race of space travelers will find one of the spacecraft and read the map to learn where it came from.
A sufficiently intelligent alien could figure out where we are by measuring all these same pulsars and figuring out where we are in relation to them, because each pulsar has a unique period.
The unique spin of each pulsar also makes them super accurate astronomical clocks, keeping better time than the best atomic clocks here on Earth.
Pulsars are so accurate because they're nature's ultimate flywheel. This is an ordinary bicycle tire mounted on a repair rack here in this bicycle shop. And this wheel is very much like a pulsar. Let's give it a spin. So you see the wheel is rotating very smoothly. There's very little to slow it down. Now for a pulsar in space, there's almost nothing to slow it down. Now notice that the wheel is rotating about a couple times a second. That's the average speed of rotation for an average pulsar. Now, of course, this wheel is only a few feet across, whereas a real pulsar is spinning at the same speed, but it's the size of Manhattan.
But nothing is forever, and even pulsars slow down over time, although they do it very slowly. The same bicycle wheel that illustrates the pulsar's spin also demonstrates what makes it slow down.
Pulsars convert rotational energy into radiation, and in the process, they have to slow down. Let's see how it works with the bicycle wheel. Now, the wheel is moving pretty quickly. If I put my hand to the rim, I can convert rotational energy to heat energy in my fingers. Ouch. Now the wheel has slowed down. In a real pulsar, it would be more like the action of a feather than my hand, because pulsars lose energy very, very slowly.
A pulsar, spinning once every second, may slow down by about only 3/100ths of a second in a million years. Occasionally, though, a pulsar may actually speed up slightly. In a phenomenon linked to a neutron star's crust, a layer of matter 10 billion times stronger than steel, and yet subject to starquakes.
Neutron stars are not solids all the way through. They have a crust, and that crust is incredibly strong. But there are forces within the neutron star that can occasionally cause the crust to crack. And when it cracks, the whole neutron star readjusts itself, and it produces a change in the rotation of the neutron star. We call it a glitch. The crust has cracked. There's been a starquake on this neutron star.
Though the strange world of pulsars includes intriguing events like glitches and starquakes, you'd hardly know it from the tiny blinks seen when they're captured by telescopes. But what happens when pulsars are hurling deadly radiation into cosmic clouds after their parent stars have ripped holes in the galaxy with their massive explosions in space? What will their impact be on any living beings in their path? The deadly explosions of supernovas are endlessly fascinating. They are the violent screams of aging stars outraged at having to grow old. The powerful blasts would do more than kill any living beings in their path. A supernova would wipe out all traces of any civilization on a planet in orbit around the exploding star. The galaxy is full of the colorful after effects of these explosions. They are gigantic clouds of stellar debris called supernova remnants. And if you're searching for a pulsar, that's the best place to look.
Pulsars are actually found in supernova remnants. That's because pulsars are formed in a supernova, an exploding star.
While some pulsars speed away from or simply outlive their supernova remnants, others remain spinning inside them. There, they light up the surrounding shell and create what's called a pulsar wind nebula.
The wind from a pulsar is not quite like we think of on Earth, which is air blowing. Instead, it's a wind made of particles and radiation. But it's blowing out at very high speeds, much faster than anything we have here on Earth, high enough that it carries a lot of energy. And the energy interacts with the material that's left over from the exploding star to cause it to light up.
By far the most spectacular example of a pulsar wind nebula that we know about is the Crab Nebula, which has a spinning neutron star at its center, and that's what energizes the whole thing.
The Crab Nebula is a famous supernova remnant from the supernova that occurred in the year 1054 AD, studied by Asian astronomers.
The supernova itself could be seen in the sky for weeks before fading away, only to be rediscovered nearly 700 years later as a supernova remnant, visible only through telescopes. The pulsar in the Crab Nebula was discovered in 1968, very soon after the first pulsar, and it confirmed the theory that pulsars came from supernovas. Seen from the Earth, the pulsar in the Crab Nebula looks like an insignificant speck. Before it was identified as a pulsar, no one realized it was actually blinking on and off 30 times a second. In a typical long exposure photo from a telescope, it registers simply as an ordinary star.
Well, 30 times a second is too fast for anyone to actually see the Crab pulsar blinking. Instead, we have to use a kind of high-speed photographic technique called a photon counter. And that's able to take pictures fast enough to actually see the pulsar blinking on and off. It appears to be on when the pulsar beam rotates toward us, and it's off when the beam rotates away.
What's incredible is the power of the pulsar. Everything we see in the Crab Nebula is glowing because of the energy streaming out of that single spinning neutron star.
The neutron star in the middle of the Crab Nebula has a diameter of perhaps 10 miles, but it's lighting up the gas around it for several light years. So this eensy-beensy thing is lighting up a tremendously large region around it because of all the energetic charged particles coming away from it.
The pulsar is lighting up a supernova remnant 6 light-years in diameter, equivalent to nearly 380,000 astronomical units. An astronomical unit, or an AU, is commonly used to describe distance in the cosmos. Will W. of Denver, Colorado, wants to ask the universe just what an AU is.
Will, that's a useful thing to know. My snappy answer is that an astronomical unit is one heck of a big apartment. But really, the astronomical unit is the average distance between the Earth and the Sun. Now, that's about 93 million miles, or equivalently 150 million kilometers.
The chaos deep inside the Crab Nebula is revealed by time-lapse pictures in both X-rays and visible light. The spinning star's pulsar wind creates shock waves around its equator, while polar jets are shooting out in turbulent streams.
So this is a very dynamic system, an exciting one, and everybody in astronomy studies the Crab Nebula.
Like most pulsars, the one inside the Crab Nebula is gradually slowing down. But about 10% of all pulsars have found a method of speeding up in a big way. They're called millisecond pulsars.
Millisecond pulsars are what we call recycled pulsars. They used to be ordinary pulsars, they stopped pulsing, and then because they were in a binary system, that is, there was another star nearby that they could steal some mass from, they are spun up, so their speed increases to millisecond speeds.
Each time something falls onto the pulsar, it gets a kick because the stellar matter from the companion swirls onto it instead of dropping straight to the surface. The rotating bicycle wheel illustrates how the process makes the pulsar speed up.
The wheel is spinning, and my hand is like the matter from the companion star. Because it has rotational momentum, it swirls inward and strikes the star like this, increasing its speed of rotation. It doesn't drop down like this.
In nature, the speeds attained by millisecond pulsars are breathtaking.
Pulsars spin several hundred times a second, even up to maybe 1,000 times a second for the fastest ones. And that's very unusual because you're talking about something the size of maybe Manhattan spinning a few hundred times a second. That would make you pretty dizzy.
Even more exotic than millisecond pulsars are the strange beasts known as magnetars.
Magnetars are extremely rare. In fact, we didn't even know about any of them until 1979, and even then we weren't sure exactly what we were looking at. Now we know of only about 15 magnetars amongst the 400 billion stars in our galaxy.
Pulsars are known to have strong magnetic fields to begin with, but magnetars take magnetism to the extreme.
The magnetic field of a magnetar is intense. It's 1,000 million times the magnetic field strength of the Earth. Now, if there were a magnetar anywhere nearby, it would demagnetize all the credit cards in the world.
But credit cards wouldn't be of much use to humans, whose very molecules may be pulled apart by a magnetar.
Magnetars have the strongest magnetic field in the whole universe. It's unclear exactly if humans could even live amongst a magnetic field that strong because the magnetism tends to pull water molecules apart into elongated structures. It's doubtful that people could even live.
And as if magnetars and millisecond pulsars weren't bizarre enough in the Milky Way's galactic sideshow, there are other freaks even more mind-blowing. What are the chances of finding twin pulsars, pulsars with planets, and pulsars joining the drummer of the Grateful Dead?
take the click off.
Meet Mickey Hart, longtime drummer who first gained fame with the Grateful Dead, and now makes music to the beat of Pulsars from space.
I wanted to interact with the fabric of the universe, the things that blew us into creation, the seed sounds. So these electromagnetic waves we've transferred into sonic waves. Pulsars are especially interesting.
Those electromagnetic waves from pulsars reach us most clearly in the form of radio waves, sweeping across the sky in the freakish beams that make pulsars stand out.
Pulsars produce a lot of radio waves, and that's quite unlike normal stars. Normal stars shine mostly at visible optical wavelengths. So when you see a bright radio source out there, it captures your attention. And if in addition it's going beep, 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 then it really captures your attention.
We're also very lucky that radio waves can make it through long distances in our galaxy without being affected by the intervening gas and dust. And they make it through our own atmosphere as well without any trouble.
But perhaps what's most exciting about pulsar radio beams is that they come from hundreds of light years away. But pipe them into a set of headphones or speakers, and we can actually listen to them.
For slow ones, what you hear is a bump out of the speaker every every rotation. But for the highest frequency ones, you hear a continuous tone.
This is the unearthly sound of a typical pulsar, rotating 1.4 times each second. Converted to audio, the pulsar's radio signal is a hypnotic, repetitious tick. But turn up the frequency and listen to this millisecond pulsar, spinning 174 times per second, so fast that its ticks blend together to generate a ragged note that's on the edge of turning into music. That's especially true when we listen to the Vela pulsar.
The Vela pulsar has a terrific rhythm to it. It's hard to imagine this sound coming from a spinning star, of all things. It almost makes you want to get up and dance.
The Vela pulsar is spinning with its cosmic beat at the center of a giant supernova remnant, where its killer radiation tears through the galactic gas and dust around it. The supernova exploded 11,000 years ago, and today the pulsar is most spectacular when seen in X-rays. Rotating 11 times a second, time-lapse photos show that it's shooting out a jet of material, whipping through space like an uncontrolled fire hose. The unusual space beat of the Vela pulsar is a special turn-on for Mickey Hart, who's now making it the basis for part of his latest project.
Well, Vela pulsar, it's really made for composition because it has a regular rhythm. And sonically, it's been enhanced, and it feels good, and you can use it in composition. So I went to the Vela first thing.
Hart used some simple pulsar sounds during the Dead's 2009 concert tour, and now he's building them into mind-bending tracks for an upcoming sequel to his Global Drum Project album. His pulsar sounds came from the SETI Institute, which leads the search for extraterrestrial intelligence.
I went to SETI, and they led me to the sounds that I was looking for. I really hadn't delved into the sounds of the universe before, and they just had the mother lode of it there, and they shared it with me, and then I turned it into music. Once all of these things started to come my way, I realized that, the universe was singing. It's a spiritual thing for me as well as entertainment. I mean, it's fun working with the cosmos. Beyond fun, it's a deep spiritual experience for me.
The cosmic chorus gets much bigger when it comes to a place called 47 Tucanae, a globular cluster of stars in the southern constellation Tucana, the Toucan. The cluster is 16,000 light-years away, with 2 million stars packed into a sphere 120 light-years across. Incredibly, 47 Tucanae has 22 millisecond pulsars, each generating its own musical note in the bizarre stellar choir. To get a millisecond pulsar producing a musical note, you need to start with the kind of pulsar whipped up in speed by matter spilling onto it from a binary companion star.
Well, in order to do this, you have to have lots of nearby stars. And what better place to do that than in a star cluster? So something like 47 Tucanae, which is a tremendously large collection of stars nearby, is an ideal place to have neutron stars turn into millisecond pulsars.
The collective tune from the cluster's pulsars is a strangely haunting song from space, generated by their 22 unique and different spins. While millisecond pulsars throughout the galaxy usually have normal stars as binary companions, there is one known binary system that's a true freak, because it has a pulsar paired with another pulsar. Discovered in 2003, the only known double pulsar formed when a millisecond pulsar's companion went supernova. And now the two pulsars orbit each other in a space so tight they would fit inside our sun. While pulsars can have companion stars or companion pulsars, things get even stranger when we realize that even after a supernova explosion, some of them actually have planets.
A pulsar is sort of the last place you'd expect to find a planet, because what happens to create a pulsar is a supernova explosion. So if the original star happened to have any planets around them, they probably would have been blasted apart by the supernova.
But in 1992, the very first planets discovered outside our solar system were found around a pulsar. The giant radio telescope in Arecibo, Puerto Rico, was used to precisely measure the timing of a pulsar 980 light-years from Earth.
It was changing, going a little faster and a little slower, and that implied that there was something else besides this pulsar itself. It was not isolated. It turned out to be, indeed, a planet.
Calculations now show there are at least 3 planets in orbit around the pulsar, and a 4th is suspected. The pulsar's supernova may have destroyed its star's original planets, but new ones formed, apparently out of debris left over from the system's explosion. Pulsars are the embodiment of extreme forces when it comes to individual stars. But what happens when you ramp up such power to the level of an entire galaxy? At that scale, we find the quasars. What makes them outshine everything else in the cosmos? And why do scientists say that in the heart of each one, there sits a monster? While things like pulsars and magnetars stand out as freakish stars in the cosmos, even stranger objects lurk much farther away, where the quasars live.
A quasar is a blindingly bright core of a galaxy that has a giant black hole in the center. And it's extremely bright. It can be as bright as 10 to 1,000 times brighter than all the stars in the galaxy put together.
This Hubble telescope photo proves just how bright a quasar can be. The two prominent objects look almost the same, but one is only a star perhaps 100 light-years away, while the other is a quasar 9 billion light-years away. Like pulsars, quasars were first noticed by astronomers as strong sources of radio waves. The very first was a radio source called 3C273.
Well, what's a 3C273? The Cambridge Radio Telescope collected a catalog of bright radio sources that were seen in the sky. And it was the third Cambridge catalog, and its item number 273 was a bright radio source. People were trying to figure out, what is this radio source?
When optical telescopes were pointed at its position, all they saw was what looked like a star.
But then when it was realized that this object was very far away, more than 1 billion light years away, in fact.
It meant that their true power, the amount of energy they put out per second, their wattage, was enormous. Because to look bright and yet be far away means that you've got to be really a powerful object. What could it be? Now, 3C273 was identified with a rather bright bluish star. So it looked star-like, but stars don't generally emit radio waves. So it was called a quasi-stellar radio source.
Quasi-stellar radio source was just too long a name, and so it was shortened to quasar, but golly, doesn't that have a nice sound?
Quasar is really a great term because it implies something exotic and unusual, and that's really what these objects are. They are huge black holes that are eating material around them and radiating huge amounts of light that can be seen almost all the way across the observable universe.
The black hole consuming galactic gas inside the quasar is so violently ravenous, astronomers have given it a frightening nickname.
The black holes inside quasars are often called monsters, and that's because they're very massive. They're 1 million to 1 billion times the mass of our sun, and they're voraciously devouring the material around them, so they're sort of behaving like monsters.
The quasar is said to be powered by the black hole at a galaxy's center. The notion of something so bright that is also black seems like a contradiction in terms.
We know that black holes are objects that are so dense and massive and have such strong gravity that not even light can escape from them. So that makes us wonder, how can black holes power anything at all? And the answer is that gas, as it falls into the black hole, can actually radiate energy before it falls in. After it falls in, it's gone. The way this happens is through friction. So if I take my hands and rub them together very quickly, that produces a lot of heat. Now, the material that falls into a black hole spirals in and rubs against itself, and it's moving at extremely high speeds. And so, in the case of a quasar, we have gas that's rubbing together and moving at very high speeds. And so in doing so, it can heat itself up to even millions of degrees, which can cause it to glow very, very bright.
Astronomers are confident that there are giant black holes in the center of all galaxies. So why aren't there quasars in all galaxies too?
To get a quasar, you need two things. One, you need a huge massive black hole at the center of the galaxy. But you also need a supply of gas to fall onto that black hole.
If there isn't enough material around, if the black hole has basically eaten all its food around it, then there's nothing to shine, there's nothing to glow. It won't be a bright quasar. So there could be, and probably are, black holes at the center of most galaxies, but if there's no fuel for them, they won't be quasars.
But there are conditions in the universe that may make a quasar reignite long after the gas in its host galaxy's center gets used up.
And one promising way of doing this is by slamming two galaxies together. We know that galaxies collide, and when that happens, it creates a big cosmic smash-up that drives material down to the center of the galaxy.
The scenario could apply to our own Milky Way galaxy, which is on a collision course with Andromeda, the giant spiral next door.
In 5 or 6 billion years, when the Andromeda Galaxy starts merging with the Milky Way galaxy, it's conceivable that enough gas will be pushed toward the central supermassive black holes that they'll turn into quasars. Now, the Andromeda Galaxy will probably be the brighter of the two quasars, because Andromeda has a much more massive black hole than our Milky Way galaxy. If Andromeda turns into a quasar when it's merging with the Milky Way galaxy, it's conceivable that it'll be comparable to the full moon in brightness when it's 10,000 light years away. Wow.
Even as close as 10,000 light years away, we wouldn't see the Andromeda quasar's disk as we can with the full moon. Instead, it will appear as an intensely bright star, flickering due to atmospheric fluctuations, as all stars do. But incredibly, if a quasar forms at the center of our own galaxy, we wouldn't see it at all. As bright as it may be, there is so much dust between the Earth and the galactic core, quasar's light would be hidden from us, while Andromeda's would light up the sky. If there is a local quasar in our future, it could take any number of different forms. They bombard space with astrophysical jets and sound like mythical creatures with names like blazars and dragons. The stories they tell lead us through the cosmological epic where we arrive at the beginning of time to find out how quasars helped build the universe at its very birth. In nearly 50 years of searching, astronomers have discovered nearly 1 million quasars scattered throughout the universe. And as it turns out, they come in a wide variety of forms.
A quasar is just one of a family of objects called active galactic nuclei, all of which are powered by material falling onto huge black holes at the center of galaxies.
The rate at which supermassive black holes can swallow material in the centers of galaxies can vary all over the place. The ones that don't glow so brightly are called active galactic nuclei, but not quasars.
One of the most bizarre features of active galactic nuclei are the high-speed jets of material shooting out from some of them. 3C273, the first quasar to be discovered, has a jet. It's only subtly apparent in the optical image, but becomes more vivid when seen by X-ray, infrared, and radio telescopes. Quasar jets are an astronomical mystery. For years, scientists have racked their brains to explain exactly how they are generated. As with pulsars, a spinning wheel in a bicycle shop illustrates the forces they believe are at work. A vertical spoke represents a force line in the quasar's magnetic field.
The jets from quasars probably require two things to form. The first is a disk of gas that orbits the black hole. The second are magnetic field lines that are anchored to the disk. Here's how we think it works. Charged particles love magnetic field lines. So the particles get tied to the field line, and as it rotates, they get blown upward away from the disk. Now, eventually, the field line will twist around, forcing the matter into a tight column, or what astronomers call an astrophysical jet.
The charged particles in the jet are moving at high speeds and can be seen from great distances. It's almost as if the quasar were trying to get noticed by doing some advertising, just as a local retailer might do on Earth.
This advertising gadget is called an air dancer. It gets our attention here on Earth like the jet out of a quasar. And in fact, the way it works is similar. The fabric rippler acts like the twisted magnetic field generated by the quasar. The air inside follows the walls of the rippler like the charged particles following the magnetic field lines in the quasar. The big difference is that here, the air is flowing maybe 50 or 60 miles per hour. In a quasar jet, the particles are moving at nearly the speed of light.
The air dancer's display also extends only 12 feet or so from its power source. A jet coming out of a quasar or another active galactic nucleus, however, stretches far into space, where it may turn into an amazing phenomenon that astronomers call a dragon.
DRAGON stands for double radio source associated with an active galactic nucleus. That's sort of a long term, but if you look at pictures of these things, dragon fits much better. What they are formed by is these jets of material getting shot out from the black hole at the center of the galaxy, slamming into the intergalactic medium in between the galaxies, and forming these massive lobes and hotspots that can extend to distances much larger than the size of the galaxy itself.
The scale of a dragon is mind-bending. The typical one is about 1.5 million light-years end to end, far, far larger than the entire galaxy that's producing it.
If the active galactic nucleus were scaled down to the size of this basketball, then the size of a dragon from one radial lobe to the other would still be absolutely enormous. It would be about the size of the entire Earth.
Most dragons are linked to quasar cousins called radio galaxies, since they are strong sources of radio waves. But other members of the same family are high-speed objects called blazars, whose jets are pointed almost directly at our line of sight, making them incredibly bright. And our line of sight actually leads us to the most amazing discovery about blazars, quasars, and radio galaxies. Who would have believed these freaks are all basically alike?
From studying all these types of active galactic nuclei, we now realize that in some sense they all can be treated as the same thing, just viewed in different ways. In particular, the important thing is the viewing angle, or the angle of the jet of material relative to the angle that we look at it.
The centers of active galaxies are all very bright, but they may not seem that way because the shining material at their cores can be partially or completely hidden.
This material we see is surrounded by a donut-shaped ring of material. That material is gas, dust, clouds, can block the light from escaping from the central region that's really the active part. And a radio galaxy is one of those in which the donut is blocking our visibility of the central core. But in the case of a quasar, we're looking down toward the hole in the donut, and that allows us to see the material right around the black hole that is the quasar. If this quasar has its jet pointed toward us, then the jet itself becomes extremely bright. This is what we would call a blazar.
All three are the same. The only difference is our point of view. But regardless of our viewing angle, one thing they all have in common is their great distance.
The thing that shocked us about quasars was how far away they are. They're so bright, and to see them that bright at that distance, they must be titanic, absolute monsters. So why are none of these things nearby us?
The nearest quasar is 2 billion light-years away. The most distant ones are 13 billion light-years away.
Most quasars are seen at vast distances from us. That means we're seeing them as they were a long, long time ago in the past, when the universe was very young. Quasars appear to be denizens of the young universe. Galaxies early in their formation seem to have produced these black holes, and the black holes still had a lot of material to eat shortly after being formed, so they glowed as quasars.
The earliest quasars date from shortly after the Big Bang itself, suggesting they had an important role to play as the universe endured its early growing pains.
It's possible that these supermassive black holes that we call quasars were part of the process of creating structure in the universe. The process is not completely understood.
So, with most of the quasars confined to the distant past, we study them intensely, hoping they'll shed greater light on the origins of the cosmos. The early giant black holes may have been among the engines that built the first galaxies. giving form to the chaos of primeval gas that would take shape in what we now see as the universe.